Today what we're going to look at is relative humidity. We're going to look at the terms associated with it and how to actually calculate it using some actual equipment. But first, before we do that, we need to talk about some science I'm sure you've talked about before, phase changes. All right, so the three main states of matter that I'm sure you've heard of: solids, liquids, and gases. All right, you can go from a solid into liquid, and that phase change is called melting. You can go from a liquid to a gas, which is called evaporation. All right, and you can go the other way. Gas to liquid is condensation. Liquid to solid is freezing. I'm sure this is all review. A few pointers, though, that may not have learned. Remember how temperature is a measurement of the thermal energy? Well, if I'm going to go from a solid into a liquid, not only do you have to warm it, its temperature, but once you get that melting temperature, you have to keep adding thermal energy into it to get it to go from a solid to a liquid. All right, the actual change from a solid to a liquid requires energy. Same thing with a liquid. You can get water, for example, up to its boiling point, all right, but you still have to keep pumping thermal energy in it to get it to go from that liquid to a gas. All right, and if you go the other way, when you have a gas, you can cool it down to its condensation temperature, but you have to it will have to still release energy to turn back into a liquid, and liquid to a solid will have to release that thermal energy when it freezes. Very important to conceptually understand that. Solids are the lowest energy state of matter of the three. Gases are the highest energy state, and it requires energy to go up, or it requires the release of energy to go down. Two other phase changes that you may not know of. It is possible to actually go straight from a solid to a gas or gas to a solid. Those terms are sublimation and deposition. All right, some other terminology that we want to know about. Saturation. Okay, just think of a sponge. When you completely fill it with water, all right, it can't hold a single drop more. It's completely saturated. Well, you can do the same thing with air. Air is completely saturated. It means it's holding as much water vapor as it possibly can. Now, technically, the air is not holding the water aloft. It's a common misconception, but we're gonna use those terms at this level. The dew point is the temperature at which the air must be cooled so that it becomes completely saturated. So when it's really, really hot outside during the middle of the day, all right, the air is not holding all the water it can. It's not completely saturated. But if you notice in the morning, all right, when it's cool, all right, the amount of water in the air never really changed throughout the night. But the air has cooled down to the point where it's completely saturated. There may be some fog outside and things like that, and we'll get deeper into that later on. But it's the temperature at which air must be cooled at a constant pressure to reach saturation. Because if you change the temperature, you can, the pressure, you can change how much moisture the air can contain. Absolute humidity. It's the amount of water vapor in the air. Okay, so this is actually measuring like, okay, there's 5 grams of water per cubic meter, or something of that nature. All right, so how much it's actually holding at that point. The maximum amount that it could hold at that given temperature is called the saturation quantity. These are measured in the same units, grams per cubic meter usually, or something of that nature. All right, this is how much it's actually holding. This is the amount it could be holding. The reason why we're going through these two terms is because if you want to talk about the relative humidity, all right, you are really describing how these two numbers compare, the ratio of the absolute humidity compared to the saturation quantity. Okay, now there's a bunch of different ways we could go about calculating this. We're going to actually start off by using pieces of equipment to measure this quantity. And the two most common ones are a hygrometer, all right, which just kind of looks like a dial, and a sling psychrometer. Let's look at the hygrometer first. So the hygrometer has got this dial, and as it becomes more humid, it goes up, and when it becomes less humid, it goes down. Now, this is kind of a black box. You're not really sure what's going on in there. So let's take a look at one of these a little bit closer. All right, a hygrometer is actually kind of interesting because it actually uses human hair or some kind of other synthetic hair to measure humidity. Now, how in the world do you do that? Well, ladies with long hair, you probably know this better than I do because I don't have any, as you know. But when it gets really humid out, your hair gets all curly and tangly and frizzy. All right, it's sensitive to the amount of moisture in the air. Well, if we took that dial-looking thing and we made it a much more simplified version, you could make something like this. All right, this is a hygrometer as well. It's a very old one, but you can see there's this piece of hair. Okay, it's being held down by a little bit of a weight, and there's this dial here. All right, this dial here. All right, there's the gauges. Well, what happens is, as this hair becomes more humid, it begins to curl and shrink, so the length actually contracts. Well, that would pull up on this dial here, causing it to register a higher humidity. As the air dries out, it would straighten out, all right, become longer, the dial would descend. So that's how these hygrometers work. Let's change it up then to the sling psychrometer. Okay, sling psychrometer, pretty simple. You got two different thermometers. That's the big thing here. All right, the difference in those thermometers is one is called the dry bulb because it stays dry, and the other one is called the wet bulb. It's got a piece of cloth that has been soaked, all right? And you basically take these two thermometers and you spin it around, okay? So let's take a look at these things in action. Okay, so what we got going on here is a couple different examples. All right, here's a sling psychrometer where it's got two thermometers. I don't have the wet bulb on this one currently. All right. But instead of using that so that you guys could easily see the temperature differences that occur, what I have is two temperature probes. All right. Connect to the lab quest, which you should see the results down in the bottom right. And as you can see, all right, one, all right, this is in red. This is the dry bulb. And this guy has been soaking in room temperature, as close as I can get it to room temperature water. All right, and they are very, very similar in temperature. Now, what happens is as you sling these things around, all right, this is again the air temperature, 21 degrees. You can see this one is becoming depressed. All right, it's dropping in temperature. And after you spin it around for about 20 seconds, all right, we can see that it's getting close to leveling out, I think. Yeah, about 18 and a half there. Well, maybe a little bit more. But as it evaporates, all right, the wet bulb cools down. All right, we'll call that 18. Okay, so now that we have got our data here, we can determine the relative humidity by following these three things. Determining the air temperature. So we had an air temperature of 21 degrees Celsius. Now we're going to use Celsius because, well, most of the other world does. The math is going to be a little bit easier, depending on how deep we go here. If you really want, you can go ahead and convert these to Fahrenheit. You know, just so you know what they are, but that's roughly 71 degrees. Okay, the difference in the wet bulb, well, it went down to 18, so 21 minus 18 is 3 degrees Celsius. Okay, and then you're going to have some kind of chart like this over to the right. We had a depression of, let's see here, 3 degrees, okay, and so that's our depression right there, 3 degrees. And then we've got a dry bulb of 21. So we just go down. And you can see here that we have a relative humidity of 75%. So it's holding 75% of the amount of moisture that it can in the air. So here's the catch. Let's try to explain why the wet bulb actually cools down. Well, remember the phase changes. I talked about how thermal energy is required to go up and thermal energy is released when it comes down. Well, what we're doing there is we have, the wet bulb is taking liquid water and evaporating it into a gas, right? That requires thermal energy, all right? And it will get that thermal energy from the thermometer. It will pull it from the thermometer. And since the thermometer itself is going to lose thermal energy, that means its temperature is going to decrease, all right? This is why the wet bulb cools down, but it's also the reason why you sweat, all right? When you sweat, all right, sweat is evaporating off of you, turning into a gas. That requires thermal energy, and that thermal energy is pulled from your body, which keeps you cool. So this idea of thermal energy being released, with the red, and thermal energy being required, being pulled from something to go through the blue changes here, is extremely important. One other little thing, it only depressed 3 degrees on that. And that is based on the amount of moisture that's already in the air. All right, the drier the air is, the more moisture it can pull, or more liquid that can evaporate, and that will pull more thermal energy from it. So it would depress even more. If it was extremely humid in here, which 75% is pretty humid, the more humid it gets, the less water will evaporate. So that will cause the dry bulb to depress less. In fact, if it was 100% humidity in here, if you can follow that, that means the air is already saturated. It can't take any of that liquid water that I'm trying to evaporate off of the wet bulb. So it wouldn't depress at all. The dry bulb and the wet bulb would be exactly the same at 100% relative humidity. So one more example problem. Jimmy uses a sling psychrometer to measure the relative humidity. The dry bulb temperature is 15 degrees Celsius. Wet bulb temperature is 10 degrees Celsius. What's relative humidity? So we know the dry bulb temperature is 15 degrees Celsius. The difference, all right, or the depression, all right, or the change, I like to use the delta for change because that's what we do in physics, is a 5-degree change. So if we go to our chart, it's going to scoot back a few slides. All right. I had a 5-degree change. All right. The dry bulb was 15. So bring them together. Means we have a 53% humidity. You won't be required to obviously memorize that chart. It will be given to you on the test or any other kind of questions. So that's everything we need to do today about relative humidity.